thanking the organizers for this very nice opportunity to present this work that I did with Pascal a couple of years ago. And now we are back to this problem. So I hope to mention some recent stuff that we are trying to do. And so here's the plan of my talk. I will first just mention a few facts about the XXZ spin chain. And later I will mention a connection between the Askey-Wilson algebra and the reflection equation. Then I will show how we can solve the so-called Heun-Askey-Wilson operator using the same technique that we use to diagonalize the XXZ spin chain. And finally, I will mention the TQ equation and how can we use this how difference Q operator to find the explicit solution of the Baxter T-Q equation. Right, so as we heard in the previous talks, the XXZ spin chain is a very important model in integrable systems. And for the case of, so we have a bulk part, right? And we have a boundary part. So the case where the anisotropy parameter delta is equal to 1 was the first one solved by Bethe a long time ago, all right? And in the case of, so this was done for periodic boundary conditions. And if we add some boundary conditions, then the solution changes a bit, and it was only solved in the 80s. First, in the case of parallel boundary fields by qRacah and others using the coordinate Bethe ansatz, and then by Schiliani using the reflection algebra. That is the technique that we are going to use here. And as we already heard about, the integrability of these quantum spin chains follows from the fact that there is an R matrix and there is a reflection equation. Okay, so the Young-Baxter takes care of the integrability of the bulk, while the reflection equation takes care of the integrability of the boundary fields. And using these R and K matrices, we can build the so-called transfer matrix, which is nothing but a polynomial of conserved charges, and it can hopefully be solved with Bethe ansatz. So here is just a picture about how the Bethe ansatz works. I think most of you here know very well about this, but let me just mention. So usually what we need to implement the Bethe ansatz, the first ingredient is a reference state, okay? And then we need a set of creation operators that we take from either from the Young-Baxter or reflection algebra. And we apply this very similarly to the harmonic oscillator. We apply this bunch of creation operators in a reference state, okay? And the eigenvalues of the quantum spin chain or of the transfer matrix, they are characterized by the so-called Baxter T-Q equation, okay, which is a polynomial equation where this lambda here is the eigenvalue of the transfer matrix. The derivative of this eigenvalue is the eigenenergy of the Hamiltonian. And all these guys are polynomials. So the Baxter T-Q equation is essentially a polynomial equation, but which is very hard to solve in general. Okay, the roots of the Q polynomial are related to the roots of the Q polynomial are the roots of the Bethe roots. Okay, an important point is that for many important models, actually, we don't know how to do the first step in Bethe ansatz, so we cannot find this reference state. Okay, and here I mentioned some of these quantum spin. Some of these models, so the spin chains with generic boundaries, which is the one I'm going to speak more about here. Okay, but like this XXZ spin chain, if you put anti-periodic boundary conditions, and like the XYZ chain, even with periodic boundary conditions, we don't really know how to build the vector for these guys. For example, the XYZ chain, we do know using this Baxter, Tatayan, Faddeev solution, the old solutions, but it's only valid for an even number of sites. And so at least for the spin chains with generic boundary conditions, okay, so yeah, so the XXZ spin chain with generic boundary conditions, it's this Hamiltonian here. So the boundary terms has not only longitudinal fields, sigma z's, but also transverse fields. And although it preserves integrability, this breaks the U1 symmetry, so we cannot find this reference state anymore. And the solution of this problem remained elusive for quite a while. There are lots of contributions. I'm not going to mention all of them here, so I ask you to go to the paper. It's all there. But the idea is that the Bethe ansatz can be modified. So this technique was introduced by Leonard and Pimenta in 2013 for the XXX chain. And then it was generalized for the XXZ spin chain. And here it's how the Bethe ansatz picture is modified, okay? So we still have some bunch of creation operators, but they are not a single element of the reflection algebra anymore. And actually we don't have, so this omega here, it's no longer a reference state of the quantum spin chain. But nevertheless, it's some state on which we can apply some creation operators and generate eigenstates of the quantum spin chain. Okay, and now at the level of the spectrum, what happens is the Baxter T-Q equation gets a new term. And this new term is called the inhomogeneous term, which was firstly discovered by Carl Yang, Shi, and Wang in 2013. Okay, so this additional term brings lots of problem for us, because most of the techniques that are used, for example, to investigate the thermodynamic limit in the standard T-Q equation breaks for this case. All right, and just another different feature is now that the number of B operators here is fixed. So contrary to the standard case where you have like, you can apply 1B or 2 or 3 and so on, here you have a number of B operators that it's precisely the length of the spin chain, it's fixed number. And so here are just to mention some open problems related to the XXZ spin chain. So the first time I wrote this slide, we didn't know how to compute the scalar product. Now, fortunately, we know how to do it, but there is lots to do. So after the scalar product, so we could express this guy in terms of a determinant formula, but up to a small factor that we still don't know how to compute, but it's not so important. And like form factors and things like that, it's all open problems. And also the classification of the Bethe roots is also a very difficult problem, okay? And now let me move to the Askey-Wilson algebra. And the idea here is that we can use this modified Bethe ansatz to solve the spectral problem of some operators that appears in the Q-Onsager framework, all right? And particularly here, we are going to be interested in the Askey-Wilson algebra, which is actually a quotient of the Q-Onsager algebra. And so let me just briefly review what the Askey-Wilson algebra is. So it's an algebra with 2 elements that we call A and A star. They satisfy this nice Q commutation relation, okay? And rho, omega, and eta star are all complex parameters, free parameters. And as you may know, this algebra provides an algebraic framework for the polynomials of the Askey scheme. But for us here, the most important point is that this algebra provides a solution of the reflection equation, okay? And so here is the reflection equation, right? We have the R matrix and the K matrix. And the R matrix is the R matrix associated with the 6-vertex model that we have been hearing about today. And here's the K matrix is a 2x2 matrix with A, B, C, and D given by the formula below. So you see that in the entries here, like in the diagonal entries, A and D, we have only A and A star. Okay, and in the off-diagonal entries, we have the Q commutators. All right, and so to build the transfer matrix, we also need the so-called dual reflection matrix, which we call here K plus. And let me just mention that this K plus has 4 free parameters. Okay, so K, K star, and kappa plus and kappa minus. So this usually it's problematic to solve this problem for the cases where this guy is non-diagonal, right? And the transfer matrix is just the trace of K plus times K of U, right? And here's the explicit expression in terms of A star, and the Q commutators of A and A star. Okay, so this operator between brackets here, it's called the Heun-Askey-Wilson operator, which was introduced by Bazayak, Chisurumoto, Diné, and Zedanov a couple of years ago. And so, as we can see, the spectral problem of the Heun-Askey-Wilson operator is precisely the same spectral problem of the transfer matrix with these reflection matrices. And the idea here is then to use the modified Bethe ansatz together with the Leonard pairs that I'm going to recall in the next slide to solve the spectral problem of this guy here. Right. So very briefly, so the theory of Leonard pairs is the following. So we consider a finite dimensional representation with dimension 2s plus 1. So s is like the spin. Okay. And we have two bases, two different bases that we are calling theta 0 up to theta s and theta star 1, theta star 2, sorry. Here it should be 0 and 1 up to 2s, two different bases for this vector space. And this Leonard pairs is as follows. So if theta is an eigenbasis of A, then A star acts tridiagonally on theta. All right. So, and the other way around. So if theta star is an eigenbasis of A star, then A acts tridiagonally on theta m star. Okay. And these constants are chosen according to the representation, right? And here we use the following parametrization of the eigenvalues. So we have theta m given by this formula here, and theta m star by a similar formula. Okay. And let me just recall that the transfer matrix in this case, it has this generic form. Okay. So we have A, B, C, and D. And for you that knows about Bethe ansatz, you know that we don't like B and C in the transfer matrix. And so this is one problem to diagonalize this object using Bethe ansatz. And the second problem is that we cannot actually find some state that is annihilated, for example, is annihilated by the C operator or the B operator. The idea then, how can we overcome this problem? The idea is to use the so-called gauge transformation, which was introduced by Cao Yang, Shi, and Wang in 2003. It's kind of it's very similar to the way we can solve the XYZ spin chain. Okay, so the idea is the following. So we introduce two vectors that we call here X and Y. So this epsilon is a parameter that can be plus minus 1. And let me, there is also this parameter M that we call a dynamical parameter. And we have two constants, alpha and beta. Okay, so these are, and we introduce our sample vectors. They have some nice closer relations. But let me just say that we are going to play with this alpha and beta to help us to solve this problem. Okay, so using these X and Y vectors, introduce new operators that we call the dynamical operators, right? So A, B, C, and D of U and M. They also depend on alpha and beta, but to avoid have notation, we do not put alpha and beta here, but they do depend on these constants. And as you can see, actually, these guys, this new A, B, C, and D, they are actually linear combinations of the original A, B, and C. Okay, so they are linear combinations of these guys here. And in terms of these dynamical operators, now the transfer matrix still have this form, okay, A, D, B, and C, all the terms, but now we have these gauge parameters that we can play with, and they can help us to solve the problem. Okay, yeah, so here I put the explicit formulas. They are kind of ugly, but so for example, here I just wanted to show that, for example, if we choose a specific alpha, for example, we can kill B or we can kill C, and we can also use alpha and beta to find a nice reference state. as I'm going to mention in the next slides. All right. Okay, and so just as an example, for example, if we take like the B minus operator, it has this form that involves all the guys. So it involves the Q commutators of A star and A and A star. Right. So in principle, we would not need Bethe ansatz to find this. We could just propose some linear combination and try to solve the spectral problem. But I'm not sure if it's very easy to get these coefficients from brute force. Right? So the Bethe ansatz give us that nice expression. Okay, and so these dynamical operators, they satisfy what we call a dynamical reflection algebra. And it's very similar to the standard reflection algebra. So, for example, the first relation here, the commutation between the B's. So in the standard case, in the standard reflection algebra, let's say the B of U and B of V, they commute. Now they do not commute because of this shift, right? So there is a shift in this M parameter. But nevertheless, it's a similar commutation relation. And also for AB and DB, it's kind of similar as well, but the structure constants are also depend on this M parameter, except by the F and G, the F and the H. So these are the two more important coefficients in these commutation relations, and they do not, nicely, they do not depend on this M parameter. And so, and as usual in Bethe ansatz, we define a string of B operators. What I mean is that we define a product of B operators that depends on the Bethe roots. Okay, so we use this notation U bar to mean U1 up to UM. Okay, so here it's U1, and the last one is UM. And there is a very specific shift here in these M parameters that it's actually very important, such that all these relations closes, okay? And we also define the second kind of string where we replace the guy at the position I by B of U. And so, okay, so I just put here the F and H functions. So maybe if you are more familiar with cinches, so these are like ration of cinches, right? And they are, as I already mentioned, they are the most important structure constants of this algebra. All right. Okay, and so what we do, it's the standard stuff in Bethe ansatz. So we apply the A operator to the string of B operators. Okay, so we have to notice this shift. So if you put M plus 2M here, what is nice is that the right-hand side, we only have A, okay? And similarly for B. And well, the idea is that when we apply this string of B operators to some reference state, we get the vector back on this side. Okay, so this points out that we are going to have wanted and unwanted terms in the Bethe ansatz. And we also have these other terms, okay, where you have this addition, this string where you replace the guy in the middle by B of U. And so so these are like basic ingredients that we need for the Bethe ansatz. And the second one is another ingredient is the reference state. And as I mentioned, for the original C and B and AD operators, we cannot find some nice reference state. But here, by playing with these constants, we can find such reference states. Okay, so we consider, for example, we consider omega plus given by the first guy in the basis. All right, for example, omega plus theta 0 star. And by choosing, for example, alpha given by this formula, we find that the C plus operator do annihilate this state. And similarly for omega plus, for B plus, but now we have to choose beta and so on. And similarly for omega minus, for the other basis, so we can define an omega minus by choosing another alpha or another beta. And also very important is that we can these omega plus and omega minus, they are eigenstates of the A plus, A minus, or D plus and D minus. So these lambdas are just Laurent polynomials in this spectral parameter. All right, so here's the object that we are trying to diagonalize. Okay, so it is Heun-Askey-Wilson operator. In general, it has all these terms, A star, and the Q commutators. But we are going to consider different situations, different cases. So the special case, it's the simplest, but it's simple, but very interesting case where you only have either A or A star. Okay. And in the diagonal case, we have only A and A star. So I'm not, I also mentioned the generic case, but actually the most important ingredients are already in this in these two cases, the special case and the diagonal case. Okay, so what we have to do now is, okay, so here we have this A and A star. We have kind of solved the inverse problem. And what I mean by that is that we have to be able to express these elements in terms of these algebraic Bethe ansatz objects, right? And so, for example, for the special case, what we can do, we can express, for example, A. We can express A in terms of the a term proportional to the identity and A minus and D minus. So we see here that this is nice because in Bethe ansatz, as I mentioned, we like expressions where we have only A and D. Okay, and the A star, and similarly the A star, we can also do a similar strategy. So, but now we have A plus and D plus. Okay, and so here is what we find. So A, it's just a sum of A minus and D minus. And when we apply these guys to some string of B operators, we see that we get wanted and unwanted terms. And the final solution is given here. So we define the psi minus, special minus, as a bunch of creation operators applied to omega minus, for example. And we get back here the theta m, okay, provided that the Bethe ansatz equations are satisfied. So what we are doing here, we are rewriting this basis. Essentially, we are rewriting this basis in terms of Bethe states. And similarly for omega plus, okay, so the other basis we get from applying B plus to omega plus. And here's the solution. The Bethe equations are very similar up to some changes in all these three parameters. And so let me move now to the diagonal case. So in the diagonal case, we have A and A star. And what happens now is that we can no longer express this. Now we have a mixture, and we can no longer express A and this sum as only in terms of A and D. Okay. And so, for example, actually, I put the expression here, and here it is. So you can see that now it involves all the guys. So it involves A, it involves D, it involves B and C, and also a constant term. And so this is, but we do have some freedom. For example, here we can set this B equals to 0, and we are left only with A, D, and B. So this is it's not yet it's not the standard Bethe ansatz because of the B, but yet it's a bit more simplified situation. Okay. All right. So what we do, so we apply these guys so we set beta equals to 0, and we apply this A and this, A and D, and also B to this string of B operators. Okay. So, but you see that when we apply these guys to the string of B operators, the first two terms we know how to handle, but here we are going to have B applied to this vector psi. Okay. And so this is the core of this modified Bethe ansatz. What happens is that, very interestingly, when you apply this B operator, to the beta vector, it also has a very it has a off-shell structure similar to the transfer matrix. What I mean by that is that we apply B to psi, okay, and so we get a term that it's proportional to psi, and an unwanted term that it's very similar to the unwanted terms that comes from the AD and DB commutation relations. And so, but this is what is also important is that this is only valid if this number of B operators is fixed to be 2s. Okay, so this is the difference. This is one important difference with the standard beta ansatz. And so by doing that, we collect all these results, and here is what we get. So if we have both A and A star, okay, here's the solution of the spectral problem. So we have the vector in term given by this beta vector, okay, and here are the eigenvalues. So the eigenvalues depend on all these constants, and importantly in these beta roots, okay. So you see that it might be seem too simple to diagonalize an operator like A and A star, but as far as I know, there is no alternative solution for such a problem. So how can we diagonalize A plus A star? And I think the only solution that we know is like via this beta ansatz solution. And the problem now is that this okay, so here's the expression that depends on the beta roots, and the problem is that the beta equations are a bit complicated in this case because there is all this term here, right? So this is what I mentioned before. It's the inhomogeneous term, and it's not very easy to solve this equation. Even I don't know. I think we can solve numerically more or less easily up to spin, I don't know, 3/2 or maybe spin 2, but after that it starts to get complicated. Okay, and so one of the motivations that we have by doing this work is trying to understand a bit better the structure of this new inhomogeneous TQ equation in a situation which is a bit simpler than the original XXZ spin chain with non-diagonal boundaries. Right, so, and let me just mention the generic case now. So now in the generic case, we have everyone, right? So we have all the guys. And so now there is no there is no way to escape, right? So we have everyone. We have to take all of them into account. And now we cannot no longer set, for example, we can no longer set like beta equals to 0 here, because then we cannot find the nice reference state. So we have to deal with all this stuff. I'm not going to mention it here, but the idea is the same. And in the end, what we are going to have is also some kind of relation where you have a B operator applied to a beta state, which has a similar off-shell structure. Okay, and all right, okay, and let me now let me move to the Baxter T-Q equation. Let me first mention that these beta equations that we just wrote, they have some nice symmetry. So you can replace ui for plus minus q minus 1, ui minus 1, similarly for uj, and also ui to minus uj. And this motivates us to rewrite, instead of using little u's, to use what we call the big U. So the big U is this given by this expression here. And actually, I don't put the details here, but one nice thing is that we can write the beta equations and also the Baxter T-Q equation, all of in terms of this big U. It's more or less like we are rationalizing the XXZ spin chain. Okay. And I think even for XXZ, I think we can do that, but we have not done it yet, right? Okay, and so let me consider the Baxter T-Q equation for the special case again. So which is this more simple case, and we can rewrite the solutions that I put here. for the special case, where is it? Sorry. Yeah, we can here write the solution in terms of a TQ equation. Let me explain how it works. So we have here, we introduce this Baxter Q polynomial now in this variable big U. Okay, and we have a similar, we have the structure that I mentioned in the beginning. So we have some polynomial in the left-hand side. Okay, we have the Baxter Q polynomial. We have some functions that are Lohan functions of this U. Okay, and here we can, these two terms here, we can interpret them as like shifted Q polynomials. Okay, as some Q difference operator acting on this polynomial. Yeah, so this is for the inhomogeneous case. So you see that we have only Q, and also and then here the shifted guys. And for the diagonal case, it's a similar structure, but the difference again is that now this M. So here actually we have many TQ equations, one for each M. And for the diagonal case, this M is fixed to be 2S. So we have only one Baxter TQ equation. Okay, and the difference now is that we have all this part here, which is like standard. Okay, but now we have this additional term, which is the inhomogeneous term. Okay, and yeah, so and again, what is nice about this case is that, so here when you solve the Bethe equation, you just solve for this fixed number of B operators M, and you get all the spectrum, but you don't know how to you don't know how to divide in sectors, and so this is a difficult that we have to deal with these cases. And one nice thing that comes out of this solution is that for the special case, at least for the special case, we can read this Baxter TQ equation as a difference equation, which is actually the Q difference equation satisfied by the Askey-Wilson polynomial. So this allows us to actually find an explicit solution of the Baxter TQ equation by identifying the Baxter Q polynomial with the Askey-Wilson polynomial. So this is this for someone that works with integrable system is it's a source of happiness, because it's usually very hard to solve Bethe equations, but when you have such a polynomial, then it's easy. You just have to find the roots of this polynomial and you get your Bethe roots. Okay, and so this is a very rare example of an explicit solution of the Baxter TQ equation. I think it's very little cases. One case, for example, I think people know the explicit Q polynomial is the case that Gilles mentioned to us, the delta -1/2. I think we can write such a polynomial explicitly, but this is very rare. So, okay, and so let me just mention now some ongoing work and some perspectives. What we are trying to do now, so first point is that there is a transformation between these two bases, the bases theta star and theta m. Okay, and the connection between the two bases, it's given by the qRacah polynomial. And as I mentioned, we can actually, these guys can be, in the special case, they can be identified as the Bethe vectors. Okay, so these bases are essentially the Bethe vectors. And our idea here is to investigate the scalar product between the Bethe vectors, which from the integrability side, we know that this is expressed in terms of Slavnov or in terms of Godin formulas, and we hope to get some nice connections between the Bethe states and the scalar product of Bethe states and the qRacah polynomials. I mean, we hope to be able to express such scalar product in terms of qRacah polynomials, right? And maybe some Slavnov formula in terms of qRacah polynomials and so on. Well, I think other thing that we can do, it's we can try to generalize this work for the case of Q-Sager, okay? And then instead of using the theory of Leonard pairs, using the theory of tridiagonal pairs. So instead of the Askey-Wilson algebra, now we would have the Q-Sager algebra, okay? But now there is even like okay, maybe I didn't mention, but in this case that we considered is like the x-axis spin chain with one side, if that makes sense. But even for two sides, like let's say we consider this for two sides, the one problem that we have is how to solve the inverse problem. So how to express A and A star in terms of the quantum inverse scattering objects, okay? And it would be very nice to maybe at least for this n equals 2 case to identify what is the Q polynomial in this case. Because like the Askey-Wilson is in the top of the hierarchy. So, and we may wonder if there are some new stuff to be discovered by investigating this generalized guys, okay? And other thing that we can do is play with this homogeneous in homogeneous T-Q equation. So one thing that I didn't mention is that we can, so usually, for example, if we take the spectral problem for A, for example, for A, so we can diagonalize it using this basis, but we can also diagonalize it using an inhomogeneous basis by just taking the limit in this case. So by doing that, what we expect is that we can relate a Baxter Q polynomials of homogeneous and inhomogeneous cases. So for the homogeneous case, we found that this Q polynomial is the Askey-Wilson polynomial, but for the inhomogeneous case, we don't know what these guys are. And also we may wonder if there are new difference equations for the Askey-Wilson and what is this inhomogeneous Q polynomial. All right, that's it. Thank you.
Thank you a lot, Rodrigo. Any questions from the audience or from online?
So you're considering the problem of computing the scalar product when the Bethe vectors are related to the Askey-Wilson polynomial. When you're not in this special case, is it still possible to say something for the scalar product, or is it?
Yeah, I guess so. From the Bethe ansatz side, we can compute it, but and this is one thing that we are investigating actually. Yeah, for the special case, it's simpler, but the main point is that there is a recent paper by Leonard and Slavnov where they propose a way to compute these scalar products from the off-shell equations. And so because the off-shell equations here have the same form as the standard stuff, so we hope that we can also compute scalar products independently if it's homogeneous or inhomogeneous.
What about Q goes to 1 or Q goes to -1? Then
I think this limit is a bit tricky, right? And so I think there's two ways to go to this limit. I think Nicola knows better than I am. And so what I mean, so I mean that would be like the XXX limit, right? And so then instead of having like for the special case, for example, instead of having the Askey-Wilson, I think Nicola and others they identified, but I forget which polynomial is it. But
we want to do it really to generalize the qRacah, and we don't find if you just like the Q equals to 1, those things not qRacah.
okay,
That's why we really generalize to get qRacah. It's not just the Q equals 1. Increase -1.
so you cannot just put Q equals 1 in this formula.
You can analyze something, but you don't analyze the generic term.
All right. Because there is the anti-commutator, right?
Yeah, exactly.
Okay.
You are just two commutators and these two guys because the same guy. So you need one arm. And if you want all the parameters.
So maybe it's a classical Young-Baxter stuff, or
Classical Young-Baxter, we get the test at 2 elements. and operators. And really, when you need to start, it's a big of last week. You cannot start from the boundary layer that you use. It's really from the dynamical things you need to start with. For the one. You cannot just take the limit of the starting point. You start at the middle point. And you really construct, like you say, it's difficult to do the things. We did that. We really say, okay, we want some dynamical things. We qRacah.
All right.
Find the function to do that. And after all the work, right? It's not just
Can I just ask? So it's been a very long day and my attention may have slightly wandered, but the Q polynomial you gave, that's the eigenvalue corresponding to the ground state.
No, it's for all the spectrum actually. Because for the special case, essentially the beta vector, it gives you a basis, and and so for each m you have a different q, right? But that gives you all the spectrum. It's for everyone. Yeah, so there is a q of m.
So the parameters that correspond to the beta roots are
sorry, I didn't.
so the parameters in this polynomial corresponding to the beta roots. I mean,
sorry. So the z it's q u squared. So the z is the beta root.
but everything looks like it's fixed. I mean, I'm just missing something. So
No,
A, B, C, D look like they're just fixed objects.
No, okay. So this is a polynomial in this variable that it's essentially big U. Okay, so it's like instead of writing the Q polynomial as in this way, you write this as a polynomial in. So when you find the roots of these polynomials, you get the UJs. So this is a polynomial in.
Okay, I can maybe talk to you afterwards, but yeah. Okay, thanks.
The different eigenstates, they vary according to m.
Sorry, Alex.
Eigenstates, what changes with different eigenstates? The value of m, only that changes.
Yeah, it's the value of m. Yeah, for each m you have a polynomial, right? And so the beta states depend on u1, u2 up to un.
So you have 2 to the n states according to this n, right?
Yeah, no, so this is a simpler case. Actually, you have 2s states. So m goes from 0. You have 2s plus 1, sorry. So m goes from 0 up to 2s. And maybe, yeah, so just clarify. So for each m, actually, you have only one beta state. So this basis is non-degenerate.
But there's no completeness.
It's complete, yeah. It's complete.
Didn't just say
Yeah, so the basis has dimension 2s plus 1. This is it's like a, yeah.
I suggest we thank the speaker again. Thank you.
Thank you.